quietly or there will be trouble.
Of course, machines can't think as people do. The machine is different.
Big! Big! What marvelous big! How gratifying! How gratifying! Why, look at that big!
I've been giving talks of this kind for a long time, and one of the things that's interesting is to watch the evolution of things since the time I first started giving talks about climate change to the general public. Just to give you a little background, when I was studying to get my PhD at the University of Colorado in Boulder, I was working at the National Center for Atmospheric Research there. And so there were a lot of folks there who were interested in climate and especially atmospheric physics, which is where I was looking at things. And I can tell you back at that time, if you went to a cocktail party and you started to talk about atmospheric physics, it was the kiss of death. Nobody cared. It wasn't anything that anyone was interested in. It was one of those things. But then when I was on the faculty at the University of New Mexico, I was commuting to work one day, and I had this little beat-up white truck, and I only had an AM radio. So you can imagine I'm in semi-rural New Mexico riding around with an AM radio, so I'm listening to Paul Harvey. And Paul Harvey made some statements that sort of jogged the back of my brain that, gee, there's some real interesting things happening surrounding what people are saying at the time, this is the late 1990s now, about climate change. And so I started thinking about ways that you could talk to the public about it. At that time, there was a tremendous amount of fixation on temperature, the temperature of the atmosphere, which is a very difficult thing to quantify. When people use the words global warming, it's a bit tough because there's much more going on in the atmosphere than just some average temperature, which is a very difficult measurement to make anyway. So what I'm going to do tonight, what I propose to do tonight, is to give you some take-homes. I'm not going to give you a repeat of any sort of movies or things you may have seen on climate change in the past. I'm just going to give you some basic ideas of atmospheric physics. How does the atmosphere, how does the blanket of air that we live in, how does it work? What are the basic machines that drive it? And then I'm going to give you some home projects, things that you can do, or if you have children, you can do with your children, to get involved with how it is climate science is done. And the reason I feel like that's an important thing to do is that climate science is unique in all of the other subfields or branches of science in the way that it's treated and visualized and sort of expected and talked about in the public sphere. And I'll elaborate on that in a little bit. But what I'd like to start out this talk with is to ask you, when you hear the words climate change, or when you hear someone mention climate change, what comes to your mind? What springs to your mind? So give it a second and think for a second. You don't have to say anything, but just think, if I say to you climate change, what do you start thinking? Well, what I'm going to run through now is a set of imagery. And this imagery is a composite of things that I found in doing some background for this. One is just imagery that comes up if you do an internet search, an internet image search on the words climate change. The kinds of pictures that come up are often surprising to me. And also the result of what we do at Western a lot of times is we take surveys of classes and ask them to write stuff down about it. So I'm going to give you a sort of a collage of imagery that has to do with people's attitudes and feelings about climate change. So tell me, or tell yourself, think to yourself, what sorts of images come to mind for you, and then which ones overlap with the ones you see. Most of these are the ones that come up first on every one of the major search engines, so they're going to be sort of, they're the images that are sort of the things you see everywhere. But again, I want you to see how that affects you. So here's one that comes up a lot. This is what comes up when you say climate change. Or this. Or this. There are these thematic things. People like polar bears. People like ice. I don't know if that's true, I'm just saying that, okay? Let you ruminate on that for a minute. So what I was wondering, but it's a theme, it's a theme. And then one that's risen up recently when I've been doing these searches. Here's one that's risen up recently. Climate change. Now, as someone who's been doing science and scientific research for about 30 years, this kind of thing is a little bit alarming to me. Now, it's not a statement about the person. It's just that when someone says climate change to me, I don't know if I would ever get here. Okay? A lot of times people will mention something like this, or this is a popular image. Or it's, but that's the state of Florida in the upper left, so this is what in the scientific parlance is called a big-ass hurricane. Or this. Sometimes people think of stuff like this. This is one of these iconic graphs that have been around a while. It's it's one of them. It's actually not exactly that. It comes from a different place, but the basic idea is the same. Some people think about that. Okay, here's some things being said in the last couple of weeks. Okay, let's think about this for a minute. Now, I'm not putting this up here to make fun of Sarah Palin. That's not my point at all. There are some important ideas in here, okay? And there are some important things that I want to try to steer towards tonight. So if you say, what are we being fed from the science community? Well, I would hope we're never being fed from the science community. And if that's the case, then people like myself are doing a really bad job, which is probably true. That we do not do a very good job of talking to people about what it is we do. Otherwise, we wouldn't have nearly the issues that we have. Okay? Now, my goal here tonight is not to tell you what to think or how to think or anything like that. I'm just going to give you a set of tools that you can walk out of here and use. And here's another important quote that means a lot to me personally, because this is the kind of thing that I like to talk about. There's something special about the word climate change. In particular here we say, I've never seen claims of the sort that gravity people are engaging in indoctrination, right? Or the indoctrination of cell theory, the indoctrination of soil science, or the dogma of electrons. So there's something special about climate change and climate science. And Chris Kolos, who's a scientist at the University of Albany, also adds the evolution to this debate, but we're going to stay away from that one tonight. We're going to focus on climate change. Okay? All right, so one of the problems is that we do not do a very good job of talking about what science is and what science isn't. This is maybe one of the most important things we could possibly do as professional scientists, is make sure that people understand what it is we do, that it is not just a list of people, and I've listed a particular group there because those are the people who got us started, but it's those people and it's us. And it's very important that we understand that. This isn't something that a select group of people do and then come and talk to you, even though it looks that way even tonight, that that's how it works. Okay? That's not the idea. The idea is that there are important things that exist outside of all the other stuff we do, which I just spilled my water. I'm sorry for whoever has to clean that up. Okay? So there's something amazing out there. Watch this. Okay? It's a little magic trick for you. What, no applause? does that work? There's nothing here. And the thing is we have a tendency to forget just how amazing that is. But what's most amazing about that is that I can do it, you can do it, you can take measurements, I can take measurements. It doesn't matter what my political thoughts are, my political beliefs, my religious background, all of my incoming biases, none of that matters. I do the same thing as you do. We take measurements over and over, and we build on it, and we say, this is what we see happening. It's important that that basic building block right there underpins everything else that we do that we call science. Nature is the final authority on what nature does. And our job is to make observations and to make connections between those observations such that anybody can do it. Anybody can do the same thing and get the same answer. That's the whole point of it. It's not a dogma. It's not a religion. It's a way of knowing. And if we could start from that framework and we could all practice it, it really doesn't matter what else we think about or we believe or whatever we debate about. If we had that underpinning for what we do, we can go a long ways toward clearing up a lot of misunderstandings. I put up the words comets and eclipses here because the same kinds of things were going on back in Newton's day that we have going on today with climate change, except that it was about things like comets, auroras, and eclipses. Those were seen as things that were omens and intervention by supernatural powers. In every single culture on the planet, that was true. Until we started using powers of observation, powers of model building, the application of mathematics to the models. When we started to be able to predict when the comets would come and where they would be. When we started to be able to predict when the eclipses would come and when they would be, how it all worked, we started to make progress in this notion of looking, observing, modeling, understanding. Okay? So I'm hoping that eventually we can all come to that piece of understanding when we talk about climate science. Because there's a lot to do yet. There's a lot that's been done, but there's a lot to do, and we need folks to do it. All right? So what I'm going to do tonight is walk through some basic mechanics first, get us all on the same page with some basic stuff, and then show you how to build an atmosphere and build the climate from there. Okay, first of all, we're going to be talking about the atmosphere as a whole. We're going to talk about global atmosphere as a whole, the atmosphere-ocean system as a whole. Weather, on the other hand, are individual events over short time scales and short length scales, whereas climate is average events over long time scales and long length scales. So that's a big difference between what we call climate and what we call weather, which is why those photos of tornadoes and hurricanes, those are weather events. But climate is an average over those kinds of events. So I want to make sure that our framework is steady here. So first of all, force, inertia, acceleration. And then I'm going to come to this word energy, which is the most important word we're going to take away tonight, because it is really global atmospheric energy content that matters. The temperature isn't so important. None of that stuff is as important as energy. So first of all, we have to agree what we mean by energy. So first we start with force. We all sort of have an intuitive notion of what we as physicists know as force. Force is what happens when you interact two bodies, at least two bodies. It requires at least two bodies to have a force to exist in the first place. So if there were a tennis ball alone in the universe, there would not be any forces. So a force is something that's exerted by one object on another, like I'm holding this book, I'm pushing the book, I'm throwing the book, I'm exerting forces on the book is exerting forces on me. What the forces do is they cause a change in the motion, they accelerate the body. So if it's sitting still or if it's going at a constant speed, the force changes that. It changes the velocity, it changes the position, it accelerates it. Okay? Now, once you have forces, you can start to talk about what we mean by energy. Energy is a quantitative thing that it's not really, oh, gee, I woke up this morning, I didn't have much energy. It's not like that. It's a quantitative thing. It's got numbers associated with it. And so, but I can also appeal to your intuition about energy. Okay? We all understand energy, we just don't know we understand it. Now, here's my book again. All right? Watch this. Why is she so scared of me?
I don't blame her.
Why? Nothing's happening. Nothing's moving. There's nothing going on.
Potential.
Yeah, there's the potential for her to have a skull fracture. Okay, what that means is the book contains something. We call it potential energy. If I were to let go of it, it would change from potential energy to kinetic energy. Kinetic meaning in motion, so the energy of motion. And therefore, in stopping it, her head, there would be work done on her head, mechanical work done on her head, forces times distances. And that's why she's afraid. She's afraid because she knows the book has potential energy when it's just sitting there. That's one form of mechanical energy. Kinetic energy, the energy of motion, is another form. And we're used to the fact that there's a balance between these, that there's a conservation of energy. The energy stays the same. I have a lot of potential energy into kinetic, into potential, into kinetic, back and forth. The total energy stays the same. It just changes from one form to another, from potential to kinetic, right? When it stops up here, it's got all potential energy and then all kinetic energy, etc. Now, why do you need to know that? You may be wondering, why do I need to know that? Here's why. Because you hear words like watts a lot in climate science. So let's talk about what a watt is. All right, so who's been to McDonald's? Probably not for a long time, but maybe you've been there. So imagine you have in your hand a quarter pounder. Okay, you imagining that? You feel it? It's delicious. All right, so it's in your hand. It's a quarter pounder, it's in your hand. This, my friends, is 1 meter. Okay? So if I take the quarter pounder and I lift it from here to here, if I lift it against the gravity that's being exerted on it by the Earth, if I lift the quarter pounder from here to here, I will have exerted 1 joule of energy. It takes 1 joule of energy to lift the quarter pounder from here to here. I would get back the 1 joule of energy when I let go, and that's how much kinetic energy the quarter pounder would have when it got back. Now, why am I talking about this? Because if I were to now take the quarter pounder and lift it from here to here in 1 second, so if I did the lift from here to here and it took me 1 second to do so, I will have exerted 1 watt of power. So if you ever wondered what a watt feels like, you take your quarter pounder and you go like this. That's 1 watt. So for an average person, if you were to jump or just run upstairs, a set of stairs that lifted you from here to here, the average person with an average mass around here in Bellingham, if you were to walk upstairs from here to here and do that in 1 second, it would be about 300 watts. You'd have to exert about 300 watts to do that. So watts are power. What they measure is the rate at which energy is being expended or gathered, or the rate of change of energy. That's a watt. So the reason it's important is because you hear it all the time with respect to the sun. The sun produces a lot of energy, and we're going to talk about what kind of energy it produces in just a second. But the energy striking the Earth from the sun comes in watts per square meter. So every square meter, if you lay this on the ground like this and like that, and you figure there's a square there, we can talk about how many watts per square meter is coming. And that's a very important thing because it's energy coming to us from the sun. Energy. Okay. One of the most important forms of energy around us is electromagnetic energy. It's all around us all the time. It's important. All right? How do you make it? Well, it's easy. All right? So what you do is you go home and you take your cat and you rub it on your sweater. Okay? So you rub your cat all over your sweater. What happens? Anyone tried this? Okay, so the cat gets charged up, right? So now you take your cat and you shake it. You're emitting electromagnetic waves. By shaking the charges, by accelerating the charges and shaking them around, you're emitting electromagnetic radiation. Simple as that. Now, electromagnetic radiation comes in a lot of flavors. And here's a picture. So what we call visible light, the stuff that our electromagnetic sensor detectors built into the front of our heads, they detect light in a very, very narrow range of frequencies and wavelengths. So the entire visible spectrum fits between, you see, between about 750 nanometers and just under 400 nanometers. That's the wavelength, the spacing between the repeat distance of the light wave. So again, that's shaking your cat pretty hard, but that's the idea. And you see that just to the long wavelength end of that is what we call infrared. And you're very experienced with that too, because you've been around a campfire. You've been around a campfire? So when you put out your hands, or better yet, when you put out your butt, right? What you feel is the energy coming from the chemical burn in the campfire in the form of infrared radiation striking your skin. And your body is a terrible thermometer, but it's a really good energy flow indicator. When you say, I'm getting hot, what you're saying, your body is telling you that energy is coming into your skin faster than it's giving it off, and your body's having a hard time maintaining its temperature. When you're cold, the opposite is true. So when we have things like wind chill, when you say the wind chill factor, what you're saying is that if I have a loss of energy through my skin, if I blow cold air across, I get evaporation from my skin, and I'm taking the heated air just above my skin and I'm moving it. So I start to lose energy faster when you blow that over. So what you call wind chill factor is what happens when it's the equivalent amount of energy lost through your body as though the air temperature, the still air temperature, was much lower. So if it's 10 degrees outside, and the wind is blowing, when you say it feels like it's zero, what it means is it would be the same energy loss rate out of your body if you were outside in zero as it is in 10 with the wind. That's really all there is to it. We're energy loss and gain monitors. That's what our bodies are. Okay, so we're very good, especially with electromagnetic radiation. You can really feel infrared radiation on your skin. Hold your hand over a burner, right, or a fire. What you feel, that sensation, is electromagnetic radiation bathing your skin. That's what it is. Okay? Now, everything is a light bulb. So first I have to talk about temperature in some real way now. So temperature is a device that measures something. What does it measure? It measures the kinetic energy of all the little things that make up the object that you're taking the temperature of. The little atoms and molecules that make it up are shaking, like my cat. And they're emitting electromagnetic radiation. So the hotter something is, the more electromagnetic radiation it gives off, and so on and so forth. So everything is a light bulb. Everyone in this room is a pretty good sized light bulb. You emit really well in the infrared because of your temperature of about 100 degrees Fahrenheit. You're giving off electromagnetic radiation based on that that's peaked in the infrared. You can't see it with your eyes, but you're giving it off. You're a light bulb. Okay? Everything's a light bulb. Even the background space itself in the universe, the empty space emits electromagnetic radiation because it's got some temperature. This is the background radiation that's left over from the Big Bang. I want you to meditate on this image for a minute. I apologize to the vegetarians in the room. Why do we rotisserie chicken?
Some might say we're sadistic, but you might probably want to know that it's getting all of the parts hot enough.
I'm warming the whole damn thing with heat from one side, right? And it works pretty well. If you turn it at the right rate, it gets uniformly warm. Well, here's the sun and the earth. Now, here's a little exercise you can do, and I warmly recommend this little exercise. You take a basketball and a standard BB. The basketball is the sun, the BB is the earth. And if you were to do it to scale like it is in real life, you would get about 80 feet apart. So you have to get a friend. The friend holds the basketball, and you take the BB and you pace off 80 feet. And then I want you to stand there and look at that. It's actually quite remarkable. I do this with folks all the time up at Western when we stand around Red Square with a basketball and a BB, and you stare at it, and it gives you this incredible feeling for the vastness of just the tiny region of our solar system that we live in. This notion that, wow, that's a lot of space, and we're this lost BB, you can hardly see it. When you're standing at the sun, you cannot see it. When you're standing with the basketball, you can't see it. But at any rate, so there it is. But I want you to give you that sense of scale. But the idea is, here we have a rotisserie. The Earth is rotating on its axis. That's why we have day and night. It's a rotisserie. It's being bathed in a lot of electromagnetic radiation from one side, but it's turning around like that chicken. So it warms uniformly. So if we start out with no atmosphere at all, we can do a very simple exercise and figure out what would be the surface temperature of the Earth if there were no atmosphere. What happens is there's an energy balance. The amount of electromagnetic radiation coming into the Earth from the sun gets absorbed by the Earth. The atoms start shaking. They start emitting radiation. And finally, we come to an equilibrium where the amount of radiation being given off by the Earth is equal to the amount of radiation being taken in from the sun. That's a balance. And if you do that calculation, it's not really that much colder here. The surface temperature is only about 30 degrees less on average. So that's not a lot. That tells you mostly that there's a lot of energy coming from the sun. That's what you gain from that. So now if we start building in an atmosphere, what do we get? Let's start with just a basic static atmosphere and look at some of its properties. Let me give you a gut feeling for the air around you. So it's a bunch of air sitting on top of a bunch of other air. So what happens is, just like this photo, the air at the bottom has a lot of air laying on top of it, so it gets crushed. So consequently, there's a lot more dense air at the surface than there is higher up. So there's this profile that it goes up and it gets very thin. And in fact, one of the things that shocks many people is to discover just how thin the atmosphere is. If you had a stick, okay, imagine a stick like this one, except that your stick reaches from here to Marysville. Anyone know where Marysville is? Okay, so if you have a stick that reaches from here to Marysville and you stand that thing straight up, it's going to be sticking out of the atmosphere into space. Okay? So another way to visualize that, if you imagine the Earth as a basketball that's 4,000 miles in radius, so 8,000 miles in diameter, the atmosphere is only about 50 miles thick. It goes out to 100 miles, but it gets very, very thin. But what I'm trying to get through is it's really thin. There's not much there. Okay? Here's a picture of that. So you have altitude in miles on the left, and then basically this is a surrogate for density on the bottom. So this red line is the way the density falls off really rapidly as you go upwards. And you know this because when you get to the top of Mount Everest, you know you're above more than 50% of the atmosphere, and that's why it's tough to climb Mount Everest, right? So you can see that by 30 miles, you're above 99.9% of all of the mass of air that there is. Okay, so it's not much. All right, now cogitate on this. So the yellow is energy coming in from the sun, energy per unit time per unit area, watts per square meter. So I have these watts per square meter, and they come in from the sun, and this is the Earth. So what I want you to look at, especially, is that these are identical blocks. They're identical. But if you notice, this is spread over this much area on the surface of the Earth, whereas up here at a northern latitude, it's spread over much more. So the amount of energy per unit area that's coming in here is much greater than it is up here, even though it's the same light from the sun. So the Earth heats differentially. It heats a lot more at the equator than it does at northern latitudes. And you're saying, duh. But I wanted you to have the picture of why that happens. Okay? Now, given the picture of why that happens, here's what happens. So you have a blanket of air being heated much more at the equator than it is being heated at the northern latitudes. So what happens is the air here heats, and when it heats, it becomes less dense. It expands and becomes less dense, and so it rises. And as it rises, it'll flow toward the cold areas at the pole, and so along the surface, so the rising air goes up really high and heads toward the poles, and the polar air then slides in underneath it and sets up these giant convection cells. Okay, so if this were just a static atmosphere with just heating and uniformly from all around, this is what would happen. We'd get this. Okay, we don't quite see that, and the reason is because, well, we're on a rotisserie, which means we're turning. The Earth is turning around. And there's this fascinating effect called the Coriolis effect. Oh, thanks so much. Now, these are just schematic pictures, but the reason we get winds that prevail. So we all know here in Whatcom County, most storms come at us from the west, which is true of everybody. Okay? Now, why is that? Well, here's the reason. All right? Imagine you're on a merry-go-round. So you're on a merry-go-round. And you're standing at the rim of the merry-go-round. I know we don't have merry-go-rounds at playgrounds anymore. I realize that, but pretend with me. Okay? When I was a kid, they were everywhere and they were awesome, let me tell you. So you're standing on the rim of the merry-go-round and someone is standing near the central axis of the merry-go-round. Now, you both go around all the way around the merry-go-round at the same time. So you're just going around rigidly on the merry-go-round, right? But if you're on the edge, you have to go a lot farther. The distance around the rim of the merry-go-round is a lot farther than the distance inside. So you're going really far on the outside and not so far on the inside, but you're doing it in the same amount of time. So that means that people on the outside of the merry-go-round are going way faster than the people at the inside of the merry-go-round. So, got it? You with me on that? So now, if you were to jump into the air from the outside and head toward the middle, when you jump, you have this tremendous sideways velocity going for you. So when you jump towards the middle, what happens is you're going to miss. If you're heading right for your friend, you're going to miss to the right. You're going to head towards them and it'll look for all the world like you just curved off to the right because you've got this huge velocity component. Going the other way, it's the same thing. If I jump from the middle to the outside, I have no sideways velocity to speak of. So as I'm jumping, I don't have the sideways velocity, so the merry-go-round rotates out from under me, and it looks like, from the merry-go-round's perspective, that I missed to the right. I'm always missing to the right. Now, the Earth is a giant merry-go-round. If you look down at the rotation axis, look down on the rotation axis, it's just a big merry-go-round. People near the equator are going super fast relative to those poor polar bears who are going super slow. So when air or anything else moves north and south, it misses to the right in the northern hemisphere. So as the air starts to go to the north, the warm air rises and goes to the north. It misses to the right in the upper atmosphere. And in the lower atmosphere, as it's coming down from the north, it misses to the left. Now, the reason why these are broken up is because the cells don't actually make it all the way to the North Pole. They don't make it from the equator to the pole before they sink again, and then it starts a new cycle. So there are cells of cycles. But what I want you to take home is the notion that the reason we have these prevailing flows of atmosphere is because of the combination of the warming at the equator and the moving of the air and the turning of the Earth. And by the way, this effect of the Coriolis drift, it's called, the missing to the right, was discovered, of course, by a guy who was a cannon dude. When they first started developing cannons that could shoot really far, they could not hit anything. And it was very, very confusing because people were very good at aiming stuff, but they would miss to the right, and they could not figure it out until this was discovered. Okay? Now, this is the reason why there are cyclones. This is the reason why there are rotations in a hurricane and rotations in storm cells. When you get a low pressure cell coming towards you, looking down in the northern hemisphere from the top, it's rotating counterclockwise. The wind around it rotates counterclockwise because all the air is rushing into the low pressure to fill it, and it all misses to the right and it spins. That's called cyclonic motion. High pressures, the air rushes away, misses to the right, turns clockwise, anticyclonic motion. So there's all these motions that are just the basic physics of the rotation of the Earth and the movement of the air. That's all there is to it. Okay? Now we're going to add this radiation theme. This is where it starts to get interesting. What we're looking at here, now let me talk you through this because it's not nearly as awful as it looks. This is a bottle of air. So imagine I have a bottle of air and I shine a light through it like this. And then I measure the amount of light that comes out of the other side of the bottle, and then I change the color of the light a little bit and measure what comes out, and I change it a little bit and I measure what comes out. That's all this is. So this is the percent of the light that's absorbed. So if everything comes out the other end, 0% got absorbed, and this would be a 0 on this graph. And if it disappeared like here, there you see it. Now you see nothing, so 100% has been absorbed. So we get this 100% absorption due to air here in the ultraviolet, and then there's this big window, which is magic window right where the solar spectrum peaks. So we get a lot of solar energy that comes through the atmosphere unabsorbed, and then there's a bunch of bumpy things, and then there's another window. Okay? Now, just to tell you that anybody can do this stuff, here's a plot I made. Now, the reason it looks ugly and all that is because I made it with Excel. I was trying to use tools that anybody can have, okay? Using data that I got from a colleague at the UW. This is just raw measurements of the solar flux, the radiation from the sun as a function of the light, of the color of the light, the wavelength of the light. The blue one is above the Earth's atmosphere. So this is the irradiance that arrives at the Earth from the sun. And then the orange one is the one at the surface of the Earth. And so therefore, the only difference is what the atmosphere does to the light. So you can see that there are these big places where the light has been simply sucked up. Now, I like to spend some time on this, even though I know it seems dull and boring, but this is important because a lot of people that argue about whether greenhouse gases have any effect, sometimes you hear the argument like carbon dioxide, it's in parts per million is what we measure. That's like completely, it's barely there. Obviously, it can't have an effect. Well, here is a band due to carbon dioxide absorption, and this is the light that would have come here had it not been for the carbon dioxide in the atmosphere. So evidently, it's a pretty damn fine absorber. Okay, so the rest of it, we got water vapor, we've got some methane, we've got some other, that's what these downward bumps are. They all correspond to the elements that absorb the sunlight at that particular wavelength, that particular color, as the light is coming in. Now, the trick is, it also absorbs it going back out. Please meditate on this picture for a minute. This is a really nice picture for us around here. This is a phenomenon that happens around here all the time, especially in the fall. In the early fall. So it's a beautiful place to live to get this point across. This doesn't work so well in many other places. I can show this slide and I have to say, yeah, this really does happen. Okay? What do you see? And where's the frost? Not under the tree. Okay, that's a good answer. So why is there no frost under the tree? I'm sorry, I didn't hear what you said. So sometimes I get people give your answer, but they give it this way. They say, well, the ground under there is protected. Protected from what?
The energy the tree gives out.
Ah, the energy the tree gives out. How's the tree giving out energy?
That's what you're here for.
Yeah, yeah, oh. No, that's not true. Anyway, it turns out that you can get this same effect whether there are leaves on the tree or not. And I searched everywhere. I used to have a picture of that. I have this one. This is a little bit better. You can still see there are not many leaves on this tree. It doesn't really matter whether there are leaves or not. The effect happens the same irrespective. So what you're seeing is this notion of radiative equilibrium. So let's talk our way through this. So the ground, everything. The tree, the ground, the sky, everything that's at a finite temperature gives off electromagnetic radiation. The Earth gives off a lot of infrared radiation because its temperature is in that range. So the Earth is radiating. This always happens. This effect happens on clear nights. So next fall when we have a clear, cold night, it doesn't even have to freeze to get the frost. It's just that the Earth will be radiating effectively towards space. And out here then, it radiates away most of its energy very rapidly, and the temperature right above the surface falls fast. Over here near the tree, the ground is radiating, but it's radiating right into the tree, into the trunk, into the branches. The tree, on the other hand, is re-radiating. It's absorbing that and re-radiating. So the equilibrium that the ground and the tree come to prevent the ground from losing energy as fast as the ground loses energy out here. It's as simple as that. No. I have some pictures that I lost, I couldn't find them, of sand doing the same thing. Okay, sorry. No, it's any matter at all. Anything that has mass and is at a finite temperature, meaning its atoms and molecules are shaking, will radiate. This is a universal effect. This just happens to be a nice illustration of how radiation affects things. Now, the reason I like to use this is because you can see it with your eyes and you can feel it. But the same thing is going on, a dynamic thing with the atmosphere itself is going on. Here's just a really, really, really schematic of it. So the idea is you have incoming solar radiation, the Earth absorbs that, it gets kinetic energy, its energy content raises, starts re-radiating to get rid of the energy to come into equilibrium. Some of that energy is outgoing terrestrial directly, some of it interacts with the atmosphere where it does the tree thing. The atmosphere itself absorbs it and re-radiates it back, and this is the thing that makes the Earth's surface slightly warmer than it would be without the atmosphere. The atmosphere absorbs some of the outgoing terrestrial radiation and re-emits it because it gains its own temperature. Now, it's very complicated, but this is the basic idea. Radiative equilibrium is a very hard thing, but this gives you a schematic picture. So this piece of the atmosphere then radiates away things in all directions, including back down to the ground. And this is the key to the so-called greenhouse effect. Okay? Does that make sense? Now, one of the things that comes up often when you ask people about climate change, probably the most common response you get from people is that, well, yeah, of course there's climate change. There's been climate change. There's always been climate change. The climate is always changing. So yeah, there's climate change. It's due to all sorts of factors like the sun. Well, let's look at that. So what does the sun do? Well, the sun undergoes a wonderful 11-year cycle. And this is what we show here. The green and purple, all that stuff, are the actual irradiance measurements. They're hard to look at. So people often use a surrogate of the sunspot count. And the beautiful thing is the sunspot count tracks the irradiance. So the irradiance is going, the sun is getting a little brighter, a little dimmer, a little brighter, a little dimmer every 11 years. Okay? That's basically the irradiance cycle. And this goes back a long ways because people have been counting sunspots for hundreds of years. So we can see it going on for hundreds of years. And probably this has been going on for a lot longer than that, but that's what we have measurements for. So that's, and this really isn't enough to do much. So I'd like to point out some of the other things about the sun that you should think about. I love this series of pictures. This is a series of pictures taken by a weather satellite, which is geosynchronous. What that means is, let me step over here. Here's the axis of the Earth, and it's rotating like this. So the Earth is going around like that. There's a satellite sitting above the equator, and its orbital speed matches the rotation speed of the Earth. So it stays in the same place above the Earth all the time. So the way you got to picture this is a beautiful picture. I love this picture. This is a picture taken in December. This is in March. This is in June. And this is in September. And remember, the satellite is fixed, so the rotation axis of the Earth is fixed like this. It's fixed like this. It's fixed like this. The rotation axis is fixed. So what you're seeing is the effect of the tilt of the rotation axis with respect to the plane of the orbit. So if the sun is sitting here, the rotation axis of the Earth is tilted, and so as it goes around the sun, we get seasons, because here in December, this is north is down, it turns out. Sorry, I couldn't flip the photo. But this is summertime in the southern hemisphere, because remember that plot with the yellow lines that went in and spread out the light. As you tilt the Earth towards the sun, that region will warm. So you get summer in the southern hemisphere, summer in the northern hemisphere. But this is just a beautiful example. So tilt plays a big role. How much the axis is tilted tells us about how warm it will get in that hemisphere which is tilted towards and how cold it'll get in the hemisphere that's tilted away. Now the reason that's important is because that tilt axis is wobbling. So here are all the motions that the sun goes through with respect to a northern latitude like ours. So here is a 41,000 year cycle of tilt where it tilts. It goes between just less than 22 degrees tilted, right? And then it tilts out more, and then it tilts less, more, less. It's wobbling. So you get the notion that there's more summer sun at the poles over on this side and less over on that side. So as it's going through this cycle, it's going to drive the climate in different ways. All right? Moreover, the orbit is not quite a circle. It's kind of an ellipse, which means it has a point of closest approach. And that point of closest approach is precessing around the orbit and wobbling at the same time. So as we do that, we get a 23,000 year period of the precessional index wobble, and built on top of it are these 400,000 and 100,000 year cycles. So there are these cycles that we know about because of the orbital dynamics of the Earth relative to the sun. And you can put these together and map them against things we can look at. And again, the idea is I'm not telling you what to think here. I'm showing you what is. The dotted line is that business. So if you pick this is a northern latitude. If you pick the dotted line, that is this business of the wobble of the composite of the wobble of the tilt and the wobble of the orbit put together. This would be the radiation at a northern latitude in watts per square meter as a function of time going back over 200,000 years. Superimposed on that is the methane level in the atmosphere, and you can see that those track. They're correlated. So this is climate change. I could messy this up by putting temperature proxy data and all that on there, but it would get messy and hard to look at. What I just want you to take home from this is that there are correlations. Okay? And if you put the periods of glaciation in here, they always track these minima. So it always puts together a nice little story if you want to look at it. Now, I could have made this up. I could have drawn this by hand. No, I couldn't. I'm not that good. But I didn't. And I'm going to head toward a way that you can actually look at this for yourself, get this data for yourself, play with it for yourself on your home computer, and you can see it all unfold before your eyes. But we'll get there. I just wanted to show you that this notion that what the sun does is what's causing the climate change we see today. One thing I want you to note is right here in the present. There's a significant deviation, and I can show you later if there's time that we can blow this up and you'll see a very big deviation between that's been tracking for all these years and now it's not. So let me show you another one of the iconic graphs that I want you to take home. Forcing is a climate science word that means the difference between the energy in and the energy out. So if there's positive forcing, you're getting energy in but not giving energy out. If there's negative forcing, you're getting much more energy in than you're giving out. These are the forcings due to various things. So you can see here's the variation in forcing due to the sun's energy output. That's the 11-year cycle I was telling you. And the rest is stuff that's in the atmosphere. People talk about aerosols all the time. Talk about land use. But you can see that the forcing due to the increase in greenhouse gases sort of steps away. And this is just data. This is just plain data. There's nothing more to this. You can interpret it as you please. Okay? All right, so here I'm going to get into the home project. The National Oceanographic and Atmospheric Administration, NOAA, undertook an enormous project in the last few years where they've gathered an archive where everybody's climate data of every kind is kept on a file at the NOAA website for anybody to look at, to use, to plot, to think about, to laugh at, whatever. The point is it's there. Anybody can do it. And I'm going to walk you through one example, okay? By the way, the site is right up there. If you want to go see, it's this data access project, and literally every piece of climate data done in the last 30 years is there. So again, here's a really ugly graph made on Excel because it was made by me on my home computer. What I did was I went and I got these two ice core data sets from the Vostok ice cores. This is just raw data, folks. You can get it too. And I just plotted it on Excel. One of them is the CO2 content over the last 420,000 years. And what I did was I plotted on top of it the temperature proxy, the isotopic temperature, which I'd be happy to talk about. I can tell you exactly what that means. But what's remarkable about this is just raw data. I'm just plotting it. I'm just putting the numbers on a graph. I'm not doing anything. And you can see that there's this beautiful correlation between an independent measurement of the temperature in the that the atmosphere was when the snow fell in Antarctica at that time, coupled with the CO2 content of the atmosphere at that time. So you can see that they track almost too good. It's remarkable. Now again, this is a correlation, not a causation. You have to be very careful with that. These two things are correlated, but this correlation does not imply causation. But it is interesting. And again, go home. There's a whole bunch of data here. I don't know how well you can read that over here, but this is from the ice core section. I like ice cores, but they have everything from lakes, pollen, tree rings, anything you're interested in. It's just the raw data. Go get it, play with it, see what you think. Now, another thing that's fun to do with your kids, well, after you've plotted this thing, you go away and you look up some events in history. Like I just went up and I looked up the Illinoisan period of glaciation, one of the periods of when glaciers were advancing in North America. There's the period. Now I just looked those years up. This is from geological data, which is completely separate from this ice core data. Look at that! So between the two heavy lines, there was a period of heavy glaciation in North America. It's unbelievable. You can do this. Now, let me just give you a really brief and then I'll let you watch your movie. Here in Bellingham, we're doing some work on how the future of climate science may be done. So on the roof of the big old tissue warehouse down across from the Sanitary Service Corporation down on the waterfront, there's an enormous tissue warehouse building. And on the roof, we have a bunch of instruments. And the instruments are taking solar irradiation, wind, precipitation, humidity, everything, all sorts of atmospheric data. And what you're seeing here is the orange things are called the direct normal incident radiation from the sun. The blue things are called the diffuse horizontal incident radiation from the sun. So we're measuring this 24/7, every day, all the time. Here's a couple of days. So you can see, like, here's a pretty good day, a sunny day, right? Over there was some sun, there was some clouds that came through, and you can see that whenever the direct light, the orange things go down, the diffuse light, the blue things go up. So we're watching that correlation. And what's going on with this data is it's being fed, along with many other stations of its kind, to a large array of computers, like a big cloud of servers, a bunch of powerful computers. And these computers are learning. They're watching the weather. They're watching a video of the weather. They're watching this data. And every day they're thinking about it. And they're learning. And they're learning to do forecasting, not from the physical model of how air goes from here to there, but just what did it do yesterday? And so these deep artificial intelligence models are doing what's called stochastic machine learning. And what we're doing is we're learning to do very accurate forecasting in very short time scales. Like we can do really accurate forecasting about 3 hours ahead. We can tell you exactly what is going to happen. And the reason that's important is if you have solar panels and you're worried, or you have a wind turbine and you're worried about hooking that up to the grid, you need to know this stuff. But moreover, on a bigger scale, we watch this over years and years, and the machine learns about the climate. So when we want to talk about climate modeling in the future, it'll be these machine learning algorithms that will help us. Because there's a pesky problem, and that is clouds. Clouds are really hard to model mathematically. They're really tough. So the machines are learning how it is that cloud formation works. how it affects things, all of that. Okay? So, that's all I got for you, and I want to thank you so much for your attention, and we can have a brief period for questions. Is that okay? Okay.
Isotopic?
Pardon?
What about isotopic? Isotopic temperature? You said you would explain that to us?
Oh, yes. Yeah. So, all of that data came out of ice cores. Everyone know what an ice core is? No. Okay, so you go into an Antarctic ice sheet, and you bore an enormous deep hole in the ice. Right? These ice sheets are very, very thick. So what you do is you bore a hole, you take a hollow pipe, basically, and you shove it down into the ice, and then you pull it back out. And what you have then inside the pipe is a column of ice. And that ice goes back as long as the snowfall that made the ice sheet went back. Then you carefully take that frozen column back to your lab, and you take air bubbles. So you know basically what a year looks like. The ice core looks very much like tree rings, where there's periods of snowfall and periods of melt and periods of snowfall, periods of melt. So you can actually count the years. It's very simple. You just count the years. And you go back to a particular year and you look for air bubbles in the ice. That air bubble in the ice was trapped when that particular snow fell and trapped there. So that is a sample of atmosphere from that time. So you take that air bubble, and in there you just simply measure directly the CO2 content, the methane content. But now, what about the temperature? So what you do is you take the water that was there, and you look for two particular isotopes. One is deuterium, which is water whose the hydrogens have extra protons. It's called deuterium. So instead of the hydrogen having just a proton and an electron, it has a proton, a neutron, and an electron. So you look for the deuterium, and then you look for oxygen-18. And you say, why would I ever do such a thing? Well, because we've taken very, very careful measurements of the evaporation of water from the ocean and the deposition of snow and ice onto the Antarctic sheets. And there's a very, very powerful correlation between the ratios of the deuterium and oxygen-18 and the temperature at which the snow fell. And that we do today. We just take that measurement. There's a beautiful line that has temperature on one axis and isotopic ratio of oxygen-18 and deuterium on the other. And you just have a line. So once you know this, you just go over to the line and you read off the temperature. So what you do is you go back to your ice core and you go back in time and you look at the water and you measure the ratio of deuterium and oxygen-18. And that raw data is on the NOAA website. If you want to do that one yourself, you can. You can take the actual ratios of oxygen-18 and deuterium and calculate for yourself the temperature and make your own plot. I've done that. I've had my classes do that. It's powerful stuff because it starts to connect you in a way that most people are not connected to this stuff. All it is numbers we take by measuring. It's like saying, this seat, look, about a meter. There's nothing controversial about that. These are the same things. Does that answer your question? Yeah.
Hi. So I just moved here from Alaska last week, and I'm from the same town as Sarah Palin. So
yeah.
I know she noticed the same thing I have, where our winters are getting less and less. How long do you think Alaska has before we don't have winter at all, or is this part of like the 11-year cycle that the sun's going through?
No. In fact, what I probably failed to point out is that right now we're in the sun's insolation, the irradiance from the sun is on a downward slope at the moment, even though global mean temperature and all that other stuff is still going upward. So that's not the issue. It's definitely the climate energy content is going up. We're out of balance in the sense that the amount of energy coming in from the sun is not balanced by the amount of energy being re-radiated by the Earth. It's as simple as that. More energy is being stored in the oceans and the atmosphere. Now, one of the things that does, it makes the temperature go up. Another thing it does is it provides the energy to move the atmosphere around more than it's doing. That accounts for deeper, longer droughts, larger, colder storms. All of those large amplitude fluctuations in the atmosphere are driven by excess energy. So the Northwest and into central Alaska will very probably continue to warm for about the next 40 years at least. Yeah?
In the graphs where you show, for the one you used the example about the Illinois and glacier
Yes.
period. I've heard a lot of talk about it, and I seem to recall maybe even Al Gore mentioned it back in the day that you did point out that correlation is not causation. However, there seems to be somewhat of a predictive pattern in terms of ice age.
Yeah, absolutely.
And so it would appear, if you look at the historical data, that
So here we are in the
we're
present.
headed toward the precipice of another ice age. Where's the current data right now? Are we on the right or the left?
This is today, so this is years before today. So here's 0 before today, and here's going back in time this many years.
Right. So would you say that that is a justifiable extrapolation
Yeah.
based on the historical?
I would say that, but the problem is that none of these indicators. And let me bring one of the extra graphs I brought just to answer your question. Here's the thing that's alarming about what's going on today, to me anyway. Not to be alarmist and not to tell you what to think. So here again is the solar, the energy coming at us from the sun is on its way down. All the other indicators that used to track it forever are on their way up. So we're deviating significantly from what the climate has been doing as a unit. In other words, all the indicators and proxies, like all the atmospheric chemistries, temperatures, motions, all of it tracked for over 800,000 years, and now it's not.
So there is no analog historic in that 400,000-ish year history for what's happening.
No, there's no analog at all. Now, you have to be careful because in the very distant past, you'll often hear people say that CO2 levels, which are now above 400 parts per million. If you look on the Mauna Loa CO2 monitoring station website is live. It's just data coming in live, and you can look at it without even a human intervention. And I did it this morning, where it's about 409 parts per million. So we're quite a bit above those historical levels. And people will say it's never been this high, which is not true. If you go back into the very distant past, it was much higher. But everything was very different. And if you're thinking about what we're talking about, which is making the planet habitable for us, if that's what we care about, it's unprecedented. And in fact, if you look at this, many people will say, this period in here is called a Holocene interglacial period. So there are these interglacial periods here, and here, and here, and we just happen to have this rapid period of human development that occurred in this so-called Holocene period. And in fact, in the Middle Ages, there was a big warming period, and the Earth was pretty warm during that period. Not as warm as it is today, but it was warm. And in fact, many people would argue that that whole process allowed for humans to domesticate grains and animals that had we sort of gotten to that stage in conjunction with an ice age, it would have been delayed. That human development depended on the fact that we had this warming period. So it's not, in other words, the point is I don't think people would believe it's a coincidence. Okay, maybe one more? Yeah.
I don't get it. Is Earth a rotisserie chicken or a merry-go-round?
It's both.
Or a rotisserie merry-go-round.
It's both. Yeah, it's a merry-go-round with a bonfire next to it.
So what are we going to do about it? That's the thing we really need to know.
That's a great question. That's where all of the emotional part comes. What I'm hoping to do with a talk like this is not to offer you solutions, which is something we could do, but to offer you a base from which to start thinking about the problem in the first place. Because where we get into a morass is when we start feeling emotional. That's why those images I put up at first are the images they are. We think of climate change and we have this gut reaction with these polar bears, right? So my goal here tonight is to help to give you a base, not to try to convince you of anything one way or the other, but to give you some basic way of putting tools together for thinking about the problem. And once people have that, then it's a little easier to discuss the solutions because we can start talking the same language. It starts to make sense about how you would talk about studying carbon. How do we get carbon to come and go? That's a hard problem. Carbon is dropping to the ocean floor by the billions of tons every year in the form of dead animals, right? And hopefully it gets sequestered there. But even that kind of cycle is being disrupted. So once we have this common language and a common framework to talk about it, then we can talk about solutions in a way that make more sense. Otherwise, we're going to run into the problems that we have every day in the political arena, because it's going to take a global, significant political will to make the kinds of changes that we need to make. If we decide that anthropogenic greenhouse gas emission is a problem. But
that's been the problem I've been watching for the past 40, 50 years, is that one politician with a conservative point of view can pay for the study that he wants and he gets it, and the other scientist for the Democrats does it and gets what the Democrats want, and then they argue and argue and everything goes to stalemate. And that's the problem with the system, is that stalemate system that's created to block all true information from being shared with us and everyone else.
So that's my goal here tonight, is to provide you some tools that are available to anyone to start looking at the problem from a very basic point of view.
And that's the problem with the interpretation of the mind, because you can get, it's like that 10 monkeys 10 people in a circle whispered in someone's ear, and what's the answer you get out of it? Always different. And that's the problem with interpretation of any empirical, supposedly empirical knowledge, is the interpretation of it.
So that's why I'm going to leave you with this again.
Good old gravity.